Well, good evening, everyone. So today, let us solve one more problem on forces, resolving forces. In the previous lecture also, we saw something about resolving forces. Now, this is about understanding the length of a vector. Okay, now let us read the problem. The force F is acting on a block of weight W sliding down an incline. So let us draw an incline. This is my incline. This is my incline. This is my angle theta. Okay. The force N is a normal reaction. Now I have a block here of mass M, or in other words, the weight W. So definitely, if I draw the free body diagram, weight would be acting downwards. And he says this is a normal reaction. How does the normal reaction act? Normal reaction always acts perpendicular to the plane. Normal acts like this. And he also says there's a friction force F acting on the block. Where is the friction force acting? If the block is moving down the incline, friction force should act upwards. This is a friction force. Now let us write it separately to understand this. So, you have a block like this. You have the normal force here like this. Then you have the frictional force like this. And then you have a W force like this. Now, what is the question? Which of the following free body diagrams best represents the forces acting on the block? See, there are four options given over here. He's asking you which diagram will represent correctly. So this, most of the students do answer this as the right option is C. The reason is because it says, since the block is moving at a constant velocity, see which are the following free diagrams represents the forces acting on the block, and it says it's moving at a constant speed, which means whenever we say constant speed, the sum of the forces acting on the opposite directions should be equal. Now, mark my words. Sum of the forces acting on the opposite directions is equal to 0. This is what you should have. Okay. So if suppose if I have a force like this, F1, if I have another force F2 like this, then if F1 minus, see if this is positive, this is negative, then I can write F1 minus F2. If this is equal to 0, then definitely the object is moving with uniform velocity or constant speed. Now, in any of these diagrams, let us say in C, see, this length is equal to this length. So which means this force is equal to this force. Now, is it true that this and this are opposite to each other? They're not opposite to each other. As a result of this, definitely C is incorrect. Okay, so students fail to understand this particular part. They think that if the forces are acting opposite, if the forces are equal, okay, then definitely it should be C. So that is what has made them to give an incorrect answer. Now, in none of the cases, the forces are opposite. Now, how do I figure out which is the right answer? That's the question here. Now, towards it, if W is the force vertically downwards, see here also W is the force. Everywhere W is correct. Now, frictional force, okay, let us say, for example, let this be something like 5 centimeters. I'm just giving you an example. The length of this vector is 5 centimeters. Now, which force should be equal and opposite? If frictional force is something like 3 centimeters here, okay, there should be one more force acting here so that the block moves with uniformly, with uniform velocity. This should also be equal to 3 centimeters. Am I right? So which means that this length and this length should be equal. Or this length, what we have written here along the plane, downward plane, okay, this should be lesser than the W, right? Now let us look at options where we have. Have I drawn this vector anywhere? No way. Okay, so definitely this will not give us any clue. Okay, so we have this. Now we have this here. See, so therefore, this vector, instead of this vector, let us consider this vector. This vector should be lesser than this vector. See, here it is true, here it is true, here it is true. Everywhere it is true. Now let us look at the normal vector. If an object is kept on a ground, the length of the normal vector is equal to the weight vector. These two are equal and opposite. Now here, that is not being seen. See, it is making an angle here. So if I draw a perpendicular like this, now see, this is theta. This should be your 90 minus theta. I hope you're getting this. See, because I draw this bone downwards. This is theta, this is 90 minus theta. Why 90 minus theta? Because this is 90. So sum of the angles in a triangle should be 180. Theta plus 90 minus theta plus 90 should be 180. So therefore, this is 90 minus theta. Now this is once again a perpendicular, a normal 90-degree angle. So which means this angle should also be equal to theta. Agreed? This should be equal to theta. Okay, you can consider it like that. Or what you can do is the conventional way of inclined plane problems is that if this is the object, this is the object. So what you do is you call this as N over here. You had called this as W over there. And this angle, what is this angle? See, this if this angle is theta, this angle is 90 minus theta, this angle should be theta. So this vector is a component of this, which should be W cos theta. And thus we can now write N should be equal to W cos theta. This is something which you have done many times. Or N should be equal to, N should be equal to W cos theta. In other words, cos theta, see, theta is not 0. Theta is some angle here. See, this theta is some angle. So cos theta is less than W. Cos theta is less than 1. So thus you should have N should be less than W. Now look at options where N is less than W. So here N is less than W. Here N is equal to W, almost same. Okay. So, and then look at this, N is greater. First, let us look at N greater than W. So N greater than W. Definitely this is incorrect. But here, I think this is much larger length. This is a bit smaller length. Now you see, this has been excluded. This has been excluded. We need to look at these two. Okay. Now, the next is, now you see, this is N here. N is very, very small. When can N be very small? When the cos theta value is very small. Okay. And if this N is very, very small, then what can happen is the frictional force would be very, very large. Now you see, frictional force is given by mu times N. Okay. Mu is some number. Mu is some number. Let us say, for example, if it is 0.8. Okay. And this is N. Now, if let us say N is equal to some 2 centimeter, then 2 into 0.8 would have been equal to 1.6, which means the frictional force vector over here should be smaller than the normal force. Is this observed here? No. See, the normal force vector is some value. This value is 1.6 unit. I am just giving you an example, numerical. So therefore, this is not observed. Okay. So you see, this value could be around 2.2 over here. Okay, while this is 2 here, which means here, according to this, frictional force is larger than M. It cannot happen. Why it cannot happen? If that has to happen, the value of mu has to be larger than 1. It should be greater than 1. And mu lies between 0 and 1. As a result of this, definitely this is also incorrect. So which is the last option? This is the last option. Now let us see what all it satisfies. You see, this N is less than W. N is less than W. See, this length is much lesser than this W. And then N is greater than the frictional force vector. So all the constraints have been satisfied, right? So therefore, B is the right option. Did you notice how important, okay, we need to learn about vectors? Okay. Thank you, friends. So let us move on to the next problem, next class. So if you like this video, like, share, comment, and subscribe to my channel for other further updates. Thank you.